Hi, welcome to Lesson 6. In this lesson, we will be exploring C++ templates, the exception class, and queues. At the end of this lesson, you should be able to write a program that implements a queue, expand the queue implementation to operate with generic types using C++ templates, implement a basic exception handling class for our C++ template implementation of a queue. So what is a queue? Insertions and deletions to the queue follow the last in, last out scheme, just as a queue works at a bank. Operations include enqueue, which loads an item into a queue, dequeue, which takes an item off the queue, front, which returns the front of the queue, size, which returns the number of elements in the queue, and isEmpty, which checks if the queue is empty or not. Using random access with a tail pointer, we can achieve O1 for both enqueue and dequeue. What is an exception class? Sometimes performing certain operations causes our data structure to malfunction or to not be able to process the operation. Doing so, for example, performing a dequeue or front operation on an empty queue might just not be possible because the queue is empty. So we need to make sure that users of the class are aware of these limitations of the data structure. In such cases, we may need to throw a queueEmpty exception, which is a string given to the user that indicates the limitation of the data structure. Another thing that we will be exploring in this lesson is this notion of a C++ template. C++ templates are special C++ features. This feature allows us to declare functions and classes that can operate using generic types. For example, creating a queue of integers, or a queue of strings, or a queue of doubles. In other words, the function or class can be declared using a specific data type without having to rewrite the original class or function for that specific data type. That is, instead of having 10 different implementations of the queue, one for a double, one for a string, one for an integer, and so on, we can ideally just have one implementation of a queue, which loads a generic type into its implementation and specifically declares that queue for that generic type. Let's implement a queue using the C++ template and exception handling class. Let's begin by importing some important libraries. The first thing we need to do is implement our runtime exception class, which will implement all of the exceptions for our queue class. We define the class runtime exception. The public methods of this class will be a constructor for the runtime exception class, the runtime exception constructor will take a constant reference to an error message. Let's call this ERR. When it gets the error message, it can save it in a variable inside of this class called error message. We can create this error message variable in a private section of our class. And finally, let's define one more method which is able to return the error message to the objects of the runtime exception class if it's called in any other class like the queue class. We'll call this get message. This is what our runtime exception class looks like. In the specific case where we try to dequeue or check the front of an empty queue, we may need to define a particular queueEmpty class, which is able to return errors in this regard. Well, we could create another class called queueEmpty and have it independently construct its own methods for handling the queueEmpty exception, or we could inherit the runtime exceptions capabilities into the queueEmpty exception class. Let's do the latter. We'll create a class called queueEmpty as a subclass of the superclass called runtime exception. We can do this using inheritance. Inheritance is the capability of a class, we refer to this as the subclass, to derive its properties from another class. We refer to that as the superclass. So we can create the subclass queueEmpty and inherit the methods from runtime exception. Since this is a class, we need to have a constructor. And we can define the constructor by calling the constructor from the superclass runtime exception. Similarly, you can declare all other exception handling in terms of these classes, inheriting methods from the runtime exception class. Now we are ready to define our node class using C++ templates. To do this, we simply type the word template and define the generic type using the type name keyword. Let's call this generic type F. The definition for the class node remains the same. The two private members of my node class will be a pointer next and the generic type alum. If this is confusing, you can think of the generic type as a type like an integer or string or boolean and so on. With regards to the rest of the methods in the node class, all we need to do is define the constructor. We can define another constructor that takes a constant reference to our element, that is the generic type E, a destructor, and a getter method for the element, and since we are not creating our operator overloader as a friend of this class, it'll be useful for our operator overloader to get access to the next element of any node. So let's define that as node, a pointer to a type node of the generic type, get elem, which doesn't change any objects from the class. Recall that for another class to access node's private members, they would have to be declared a friend. Since we are implementing a queue data structure which makes use of objects from the node class, let's make queue a friend of this class. So we can define it as template, type name, with the generic class E for queue, and declare it a friend class of node. Let's implement each of these node methods outside of the class. I'll skip ahead to save time. For our get element, all we need to do is return the elem And for our getNext, all we need to do is return our pointer to the type node next. Our destructor doesn't have to deallocate anything because nothing was constructed in heap memory. Let's move on to our queue class. Just as we defined our node class using templates, we can define our queue class using templates too. However, we cannot use the same generic type f that we used for our node class for our queue class. We need to create another generic type. Let's call it E. We can declare a constructor, a destructor, a way to check the size of the queue, let's call it size, a way to check if our queue is empty. We can return a boolean for the method empty. A way to return the front element of our queue. Let's call this front. And our essential methods, enqueue, which takes in a constant reference to our generic type, E and dequeue, which takes in no arguments. It would also be useful, just as we did in other lessons, to have our operator overloader as a friend of this class. Notice how I use another type name G for the declaration of our operator overloader data type. Finally, we can move on to define our private members. And in this case, we only have 3 private members. We have a pointer to a type node called head, another pointer to a type node called tail, and a variable which indicates the size of my queue. I will skip ahead and declare the implementation spaces for all of these methods. The operator overloader follows the same principles that I discussed in my previous video, only this time instead of using null, we'll use null pointer. This is because null has been depreciated in C++11. With regard to our constructor, there's just 3 things that we need to declare, following the 3 things that we defined on line 61 to 63. This is our head, our tail, and the size of our queue. As for our destructor, all we need to do, if we destruct the queue, we need to dequeue all of the elements from the queue, deallocating each node. We can do this using a while loop and leveraging on our other implemented methods. our method size needs only return the size of the queue. And finally, our empty method needs to check if the queue is empty. And the way we can do that is by just checking if the head is equal to our null. We can do this in one line. Now let's implement our front dequeue and enqueue methods. Each of these methods require the use of our runtime exception class. For example, if we attempt to find the front of an empty queue, our code should be clever enough to tell the user that they're trying to check the front element of an empty queue. We can organize these ideas using the try and catch blocks. We can try if head is equal to null, then we need to throw the queue empty exception. The error message that we'll pass to our constructor from queue empty will be front of empty queue. If our if statement does not throw the exception, then we can simply return head. The element of head. If we do encounter an exception in the try block, that is, if we do reach the statement on line 107, our code will move to the catch section. Our catch block will take in this exception and output a message to the user saying front of empty queue. If no exception occurs, then we should just simply return the element that's at the front of the queue. For dequeue, there is a similar procedure. Well, the exception that could occur is if we attempt to dequeue from an empty queue. So let's first see if there's an exception that needs to be handled. Well, if we're trying to dequeue and our head is null, then we should indicate to the user they are attempting to dequeue from an empty queue. Otherwise, we can simply deallocate an element as we've done in the linked list lesson. And decrement our size. If our exception is encountered, then our catch block should be able to handle it. This is how we can implement our dequeue function. Finally, the enqueue function is simply an allocation from the back of a linked list. we may or may not require a runtime exception in this particular case. In the random access case, our linked list can increase in size without any specified bound on the data structure. In the array-based case of a queue, we may want to always check if our array is full, that is, the underlying data structure for our queue has space to facilitate new elements, and if not, it should be able to return a runtime exception. Since we are implementing our queue with a linked list, which is random access, we can continually expand our queue data structure without worrying about it being full. So let's implement our enqueue for our queue by adding to the back of a linked list. We can do this very simply by simply declaring a new node For more information about how to do this, please see my lesson on linked lists. We can check if the head is null, which will tell us if our linked list is empty or not. If it is, our tail will be equal to the new node. Our head will be equal to the tail. And finally, our head's next, which makes the tail next and new nodes next. Now, if our linked list is not empty, then we can simply have the tails next point to the new node and increment the tail. Remember that at the end of our enqueue, we are adding an element to our queue, which means that the size of the queue increases. Let's try to run our program. Just to see if there's any errors. G++. Q. C++. New. Many errors. Okay, let's have a look at what errors we have here. The first error says that it's on line 26, so let's go to line 26. And on line 26, we have getElem and getElem. So what we meant to have here was this one was supposed to return the element, and this one's supposed to return the next pointer. So let's change this to next. The next error, this is the same one. The next error is the size of queue. So this off, I think it's supposed to be a small o. Let's have a look. Size of queue, see, small o. And it says here that on line 147, we have a big O. So let's change it to a small o. 147, there it is. We make it a small o. Let's see what other errors we might have. All of our errors are now fixed. Let's now use our queue data structure. We can create a queue, specify our generic type. So now it's going to be string. It's no longer generic. It's now a string queue. Similarly, you can have an integer queue. You can have a Boolean queue, you can have a double queue, you can have a float queue, whichever one you like. But let's create a string queue, call my queue. This is the constructor part, if you didn't notice it. So So we've created a queue. We can now say my queue DQ. Let's see what happens. Let me just try to rearrange some windows to make this easier to see. I'll delete this old terminal. Right. And when we DQ on line 152, we get DQ from an empty queue. Okay. Well, let's now try to check the front of the queue to see if our exception methods are working. Seems as though I misspelled my queue, so let's just fix that up and rerun our program. All right, another error. So this error says on line 114, let's go to line 114. Aha, you see, we're calling front and our compiler picked up an error in our code in front, and we see that it's saying unresolved overloaded function type. So we didn't intend to overload the function type. We just forgot to put our brackets in. So let's put it in. Let's load. Okay, let me just make some space. And here we go, front of empty queue. Let's now enqueue some things. So we can enqueue, let's say my queue, enqueue Cersei Lannister. We can now print out our queue, and we can do that using, since we overloaded this operator, we can just say queue, or just queue, overload it, dereference my queue, end line. Alright, let's see what that prints out. Okay, so we've got Cersei Lannister at the front of the queue. Enqueue another one of these people. What's the other one's name? Daenerys Targaryen. Right. Let's output this part of the queue, and then let's output one more. I think the other one was called, is it Jon Snow or Jon Snow? I think it's Jon Snow. Maybe it's Jon Snow. I'm not too sure. Anyways, doesn't matter. Okay, let's just suppose it's Jon Snow. Let's see what happens. We've got Cersei Lannister at the front of the queue, then Daenerys Targaryen, then Jon Snow. Well, let's now check the front element of my queue. My queue front. Oops. Didn't return anything. We didn't specify a return type. So let's do that very quickly. You can see out my queue front and line. And here we've got Cersei Lannister returned. Finally, let's DQ some of these guys. So my queue DQ. So we'll DQ Jon Snow. We'll print out our queue. Then we'll DQ Cersei Lannister, Daenerys Targaryen, and finally we'll DQ the last one. And just to see if our exception is working correctly, we'll dequeue a third one and delete our queue. Okay. Right, so let's see, we dequeue on line 160, we print our queue, so it looks normal. We check the front of the queue. I'm sorry, we didn't dequeue, so now we just have Daenerys Targaryen and Jon Snow. Cersei Lannister is now gone. Then on line 163, we dequeue again, and we print it out, which just leaves Jon Snow. On 165, we dequeue again and print it out, and we now left with nothing because Jon Snow's out. And finally, we dequeue again on line 167, which triggers our runtime exception, dequeue from an empty queue. We allocated our queue using new, and so we have to always deallocate our queue using delete.